So today we are going to be talking about chemical reactions in everyday life. So just grab a pen over here. Okay. So these are the kinds of common chemical reactions, and you guys are going to have to know at least the word equations of these reactions, the general ones. So I'm going to start with burning. So if we are burning something, some kind of fuel, this could be a liquid fuel or a solid fuel, here's what happens. We've got the fuel and it combines with oxygen to give us carbon dioxide and water and some heat. This heat that we're getting off here is what makes this an exothermic reaction. So there will be a separate lesson on exothermic and endothermic reactions and what they do and what they mean. But this and heat bit means exothermic. It means it lets off heat. Okay. So this fuel in general is some kind of hydrocarbon. So a hydrocarbon is some combination of carbon molecules and carbon atoms and hydrogen atoms in some kind of way. You will see what I mean now. Oxygen gives us carbon dioxide and water. So here's an example. If we have propane, this is the kind of gas that we get in gas cylinders that we can use to have barbecues or all sorts of things like that. That sort of gas that we get in those tanks. In general, it tends to be propane. So if we have propane and we mix it with some oxygen, add a little spark so that it can start burning, then we can get carbon dioxide and water and heat. So propane, its chemical formula is this, C3H8. Again, you guys don't need to know this bit, but I'm putting it here so you guys can see what's going on so that it makes sense. You guys don't need to remember all of these things. So this is the equation that you guys need to remember. Fuel plus oxygen gives us carbon dioxide and water. That is your equation. Okay, so if we have propane and we mix it with some oxygen molecules, then we end up with carbon dioxide and water. So here you will see that it uses 5 oxygen molecules in order to get this carbon dioxide. So now we get to incomplete burning. So this is what happens if we don't have enough oxygen going through the burning process. So this happens in things like kilns, if you're deliberately making sure that there's not enough oxygen. It happens in cars, in the engine. If the car doesn't get enough air going through it, it makes carbon monoxide instead of carbon dioxide. So that monoxide means that we are getting CO over here. We can also get some carbon where it doesn't have any oxygen molecules over here. So this carbon is soot. So that is the black stuff that you get on the inside of chimneys, all sorts of things like that. That is soot. And when you get that, it means that there is not enough oxygen going into this burning process. So we need quite a lot of oxygen in order to get carbon dioxide. If you have less oxygen, then you end up getting carbon monoxide or carbon monoxide and carbon, or some combination of these 3 things, carbon dioxide, carbon monoxide, and carbon. Okay. So in terms of car engines, this is why having a good fuel mixture is so important. That good fuel mixture does not necessarily just mean getting a lot of power out of the car. It also means you need to make sure that you don't produce a lot of carbon monoxide or carbon, especially this carbon bit. That's the, if you're driving down the highway and there's a car in front of you and it's just black smoke coming out from the back, that means it's making a lot of carbon. It's actually really bad for the engine. It wears it out very quickly. So you want to avoid that. So carbon monoxide is a very poisonous gas. So it gets absorbed by the lungs, and then it binds with the hemoglobin molecules in your red blood cells, which reduces the ability of the body to carry oxygen. So if you have carbon monoxide poisoning, it means you have less blood cells capable of carrying oxygen molecules to the cells in your body where it's needed. And that is a very big problem. The way that carbon monoxide poisoning is in general resolved is by giving people blood transfusions and things like that. So carbon monoxide is not a very good thing to get. It's the reason why there are now filters in the exhaust systems of cars and things like that to make sure that we don't release this carbon monoxide into the atmosphere, where it can actually do harm to people and plants and everything. So now I'm going to move on to respiration. So this is the breathing process that we have in our bodies. But what respiration here means it's not literally just breathing in oxygen, breathing out carbon dioxide. Here we're talking about cellular respiration. So what happens inside the cell where it uses the fuel that it's got, combines it with some oxygen in order to get energy for the cell. So we breathe in oxygen. That oxygen gets carried in our blood to where it's needed for the cells in order to go through this process, cellular respiration. So this is what happens with cellular respiration. We've got some glucose in our blood, which combines with oxygen. And that gives us carbon dioxide and water. Now, this should sound a little familiar. I mean, we just did things that give us carbon dioxide and water. So here's what it looks like. This is what a glucose molecule looks like. It's got 6 carbon atoms, 12 hydrogens, 6 oxygens. It combines with some more oxygen to give us carbon dioxide, water, and some energy. Here, the energy is not put out as a form of heat. Here, we are actually trapping this energy in other molecules in our body that we can then utilize to use this energy. That molecule is called ATP, but it is not at all in your syllabus, but I wanted to tell you guys. So here, we don't have heat coming out, we've got energy coming out. So this should look fairly familiar to you. It looks quite a bit like burning up there. And that is because it's essentially the same process. Here, it's just a very, very regulated form of burning. So this bit is not in your syllabus at all, but I get asked this question fairly often. If you are losing weight, where does the weight go? Does that go through your digestive system and out into the toilet, or what happens? So in very short terms, this is a fairly complicated process. It's called ketosis. So what that means is that your body stops utilizing just glucose that it gets from food directly and starts utilizing the fat that is stored in your body. So this is a triglyceride. That is the fat that you get in your body. You will see there's 55 carbons, 104 hydrogens, and 6 oxygens in this triglyceride. It combines with a ton of oxygen molecules to give us lots of carbon dioxide and lots of water. So the way this actually works is the fat in your body gets converted into ketones by your liver. So it gets released from the fat cells where it's stored, goes into your bloodstream, gets converted by your liver into ketones, which goes back into your bloodstream, which can then go to your cells, and they can then use these ketones, sort of like they use the glucose molecule in the previous thing in respiration, in order to get some energy. So this is a slightly more energy intensive process for your body, that your body doesn't get quite as much energy from this as it does from just using glucose. But this gives your body a way of storing that glucose molecules that it doesn't end up using. So it ends up binding them into triglycerides, storing them as fat. So keep this equation in mind. So what actually happens is for every 10 kilogram of fat that you are burning up in your body, it takes 29 kilograms of oxygen in order to turn it into 28 kilograms of carbon dioxide and 11 kilograms of water. So where is all of your weight going if you are losing lots of fat? You're breathing it out as carbon dioxide, and it's going down the toilet or being sweated out as water. So yeah, that's where weight loss comes from. This whole bit about losing weight's not in the syllabus. I get asked this question a lot, so let me put it in there. So back to what's actually in the syllabus. Neutralization reactions. This is what happens when you mix an alkali and an acid. So in general, this is the equation you guys need to know. An acid plus an alkali gives us a salt and water. A salt, in this sense, is a metal combined with some kind of non-metal. And this is those ions that I talked to you about when we did the naming of chemical compounds. So the metal would be positively charged and the non-metal would be negatively charged. They would attract each other and stick together in a molecule. So here's an example. If we have hydrochloric acid and we combine it with sodium hydroxide, then we end up getting sodium chloride and water. So here, remember the chemical naming thing. Hydrochloric means that what we have is that hydrogen comes from being an acid. Acids always has an H in front. And the Cl comes from hydrochloric. That is that one group that has all of the different kinds of things that we get. So hydroic means we just have the Cl over here. This, because it's hydroic, becomes chloride. So just the single chlorine atom there. And then you just literally swap this front part. So the sodium now gets stuck with the chloride, and then this H combines with the hydroxide over here to form water. So this is essentially what happens with acids and bases reacting. So here is another example. This is vinegar and baking soda. So vinegar has acetic acid in it, and it's acetic acid mixed with some water in order to get the vinegar. We've got baking soda, that's sodium bicarbonate. So our vinegar, our acetic acid, plus our sodium bicarbonate becomes sodium acetate. That acetic becomes acetate over there. And so sodium acetate, water, and carbon dioxide. Where does this carbon dioxide come from? So this specifically comes from this reaction. So sodium bicarbonate has this bit here. So if we looked at our equation over here, we had this OH combining with that H over there to give us H2O over here. So that's what's happening here. What's happening is we've got this H going to combine with these over here, this H and the CO3, in order to give us H2O and CO2. So that's why we get carbon dioxide here. This is the reaction that takes place with all of the fizzy tablets that you put in water. This is the reaction that you get with vinegar, baking soda, things like that. So this part of our acetic acid goes directly to over here. That's our acetate. It stays. So it just gets combined with the sodium. So what do you guys need to know in terms of this? You guys need to know this equation. Wait. This equation is what you guys need to know. You guys need to know the general equation of each of these things. Then you guys need to know the naming conventions that I went through the other day in terms of what happens. Because then you will know how to combine the words in order to get your equations from that. You don't need to know these. Any of these things with the symbols, you don't need to know. I put them there because it makes more sense. You guys can look at it and go, oh, that's how it works, and then completely forget about the symbols. That is perfectly fine by me. Okay. So, displacement reactions. This happens when we have some kind of salt, again, not normal table salt, this is some kind of metal combined with a non-metal salt, so chemical salt, dissolved in water, and then we add a metal to that. So here's our example. We have copper, just plain copper. It could be a penny, it could be a copper coil, a wire, or something. And we add it to silver sulfate solution. So this silver sulfate is dissolved in water. And what happens is this copper and this silver change places. So we end up getting copper sulfate and silver. And that is the reaction that takes place. This is how we get silver-plated objects. So they would put some kind of object, maybe it's a fork or something, that they have coated in a very thin layer of copper into a solution like silver sulfate. What would then happen is the copper would go off of the metal and replace the silver atoms in the solution, and you would end up getting copper sulfate being dissolved in the water and silver being deposited on the metal thing that you put in it. So this is how we get silver-plated objects. This is one of the different ways that they actually go about silver plating things. The other one is called electrolysis. So this is one of the ways. Again, here's the chemical equation. You guys can just see that this bit changed to copper, and then the copper that was single changed to that over there. Don't bother about the rest. Okay. So our next kind of reactions that we get is oxidation reactions. This is rust or corrosion or tarnishing. It has many different names. What happens is it's some kind of metal that combines with oxygen, and then we get a metal oxide. So for example, we've got iron and oxygen, which gives us iron oxide, which is rust. Okay, so iron oxide is that brownish substance we get on the outside of some iron things, and that's rust. It slowly eats through the metal, this reaction, because there is oxygen in the air that will continue reacting with the metal that you have. So you will continue getting rust until it's completely rusted through. This is why if you have some kind of iron objects, you want to essentially coat it in something like paint or something else. They galvanize iron objects very often, just because that galvanizing adds a layer of something else on top of the iron that won't react with the oxygen. And so you protect the iron. So salt water acts as a catalyst for rusting. So things rust a lot faster if you live by the sea, because there's salt water in the air, and that ends up speeding up this rusting process by a lot. So this one was just with iron. Iron oxide is called rust. The rest of the things we called something else, corrosion or tarnishing or something else. So silver tarnishes by getting a thin black layer all over it. And when you're polishing silver, what you're actually doing is you're rubbing away this thin black layer in order to expose the silver underneath so that it's nice and shiny again. Copper corrodes and it gets this greenish blue layer on it. So I have a picture over here that I can share with you guys. So this is some copper pennies that have been found in the ocean. Again, salt water speeds this up. And this bluish color, blue-greenish color things that you get on top is essentially the rust of the copper, but it's called corrosion. So this is the copper corrosion. So that's the bluish thing. Here we've got some silver, and this darkening over here, this little blackness over here is what we call the tarnish of the silver. So if you now go and you take a cloth and some polish and you rub it off, you will end up getting the bright gleaming silver underneath this blackness again. So that's what that looks like. So oxidization doesn't just happen with pure metals just standing there as metal objects. It also happens in terms of other things. Here's a few examples: bananas, potatoes, apples, avos. These are all things where if you cut them and you leave them, they end up going brown or slightly blackish or something like that. So that reaction that makes them go brown or black on their surface is an oxidization reaction. So that's what's happening with those. If you want to make mashed potatoes and you want to cut the potatoes the evening beforehand so that you don't have to essentially be cutting potatoes the next day when you're actually trying to hurry up and make the dinner, is you would have to peel the potatoes, cut them up, and then put them in a bowl, cover it with water. That water will prevent it from reaching oxygen, will prevent the potato from reaching oxygen, and you won't end up getting that brownness that potatoes get. So there's ways around it. Other ways, especially with avos and bananas, is you can cover it with a very thin layer of lemon juice. That acidity in the lemon juice will prevent the oxygen molecules from touching the metal inside our fruit and things, and it will prevent it from going brown. Okay, so again, the equation you guys need to know is this one. Metal and oxygen gives you a metal oxide. That is our rust reaction. Okay. So metals and water. Not all metals react with water. The ones that do is the alkali metals. That is, I believe, group 1 on the periodic table, if I'm not wrong. Yeah, group 1. So the alkali metals react with water very severely in some cases. So we've got an alkali metal, it reacts with water, we get a metal hydroxide, that is a salt, and we get some hydrogen gas and some heat. Okay, so sodium, potassium react fairly violently with water, especially if you use large quantities. Calcium and magnesium react very slowly with water. You can submerge them in water and you would just get little bubbles coming up every now and then. So I have some videos to show you guys about this, but considering our time, I think I'm just going to be showing you guys one of them because we still need to do metals and acids. So let me just go there. Okay. Okay, here we go.
If we continue down the column for potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution.
Okay, So that was potassium and water reacting. This is what happens if you add a lot of potassium to water.
Yep.
Ready?
Yep.
Okay. So, that was alkali metals reacting with water. So back to over here, we are now going to move on to metals and acids. So here is the equation that you guys need to know. A metal plus an acid gives us a salt and hydrogen gas. Again, this is a chemical salt. So here's our example. We have magnesium that we combine with hydrochloric acid. That hydroic, if you remember from your chemical naming, becomes an ide. So we have magnesium combining with that. So we've got magnesium chloride and hydrogen gas. So that's how metals and acids work. And I think that is it that I have. So in terms of that, I'm just going to show you guys a displacement reaction very quickly. So here we go. So here he's got an iron nail, and he has some iron and copper sulfate mixed in there. So iron sulfate. So he's adding the iron to the copper sulfate, and it's going to give us iron sulfate and copper. So if we wait 10 minutes and we then take out the nail, he's going to hold it over the paper. So you will see that there is a layer formed on top of the iron that is the copper. Okay. So he's going to continue this with copper and silver nitrate. There he adds some silver nitrate. So after a few minutes, he skipped over that very quickly, you can see that quite a lot has been added to this copper wire, and that is the silver that has formed. Okay. So that is essentially it for today. So quick recap, you guys need to know these general equations. You guys don't need to know anywhere that I put these kinds of things. They are just to illustrate what's happening. So that's your oxidation reaction. You want metal plus oxygen gives you metal oxide. So this is the displacement reaction. Here we've got an acid neutralization. So an acid plus an alkali gives us a salt and some water. This losing weight, but you don't need to know at all. This respiration, you do need to know, you do not need to know that. So glucose plus oxygen gives us carbon dioxide and water and some energy. That is the exact same thing as our burning reaction over here. So fuel plus oxygen gives us carbon dioxide and water. And what happens if we don't have enough oxygen is we end up with carbon monoxide and carbon. So that is it for today.